Okay, perfect. Now, let me start the lecture today from the relationship which we derived on Friday, which allows us to compute the river discharge with the linear reservoir model depending on the rainfall over the catchment, which is indicated by the symbol PT here. So we are using P for rainfall. And I already mentioned to you that this P is a volume of rainfall over time and over the catchment. So it's not a rainfall depth, it's a volume of rainfall. And the difference between the two quantities is basically that in order to get the volume of rainfall over the catchment at a given time t, you have to multiply the rainfall depth by the area of the catchment. So basically, if we call RT the rainfall depth and the dimension of a rainfall intensity in terms of rainfall depth would be then a length over time, because this is depth of rainfall per unit time at a given time t. So the dimension is depth of rainfall, which is a length over a time t, because it's rainfall per unit time. If we want to compute it, translate it in terms of volume of rainfall over the catchment at time t, this is equal to the RT times the area of the catchment, and the dimension then of PT is a cubic length over time. So basically, when you compute this integral, the important thing that you have to notice here is that P tau is volume of rainfall per unit time over the catchment at time t, in this case at time tau. Okay? And this is something that is also understandable if you make a dimensional analysis of this relationship, because you may remember that K has a dimension of a time. So basically, K multiplied by d tau is dimensionless, and therefore the dimension of PT, which is cubic length over time, is the same dimension than the river discharge, which is, again, it's defined as a volume of water per unit time, and therefore, again, it's a cubic length over time. So basically, if you make an analysis of the dimensions of this relationship on the left-hand side and right-hand side, you recognize that indeed PT must be a volume of rainfall over the catchment per unit time. Is this clear? I just wanted, because I said that at the end of my lecture on Friday, so I just want to make sure that it's clear what PT is, which is a rainfall, but it's expressed as volume of rainfall over the catchment area per unit time. Please.
I have a doubt about that. I mean, by multiplying the depth or times the area of the catchment, don't we overestimate it?
Yeah, this is, this is a good question, but it's not related to the meaning that, let's say, RT and PT have. So the question is, once that we multiply the rainfall depth over the catchment, so we accept that this is a rainfall depth per unit time. Once that we multiply it by the area of the catchment, do we obtain a reliable estimate of the rainfall volume over the catchment per unit time. This means, the question means that we accept the meaning of this quantity. R is a rainfall depth per unit time, and P is a rainfall volume per unit time. So we accept the meaning. The question is, do we obtain a reliable estimate? And the answer is, the estimate is reliable as long as it's reliable RT as average rainfall over the catchment. So if RT is a reliable measurement of the average rainfall over the catchment, by multiplying this average rainfall by the area of the catchment, you obtain a reliable estimate of the volume. But of course, then your question could be, how can I obtain a reliable estimate over the average rainfall over the catchment? Because usually we have point measurements. We have rain gauges, and the rain gauge, you know what is. It's a tank, basically, that is placed outside, and it measures the rainfall depth per unit time in a given point. So the question is how to estimate then the average rainfall over the catchment. This is indeed a challenging task in hydrology, and basically if you have several rain gauges over the catchment, the task is simpler, and you can perform a spatial interpolation, and but still the estimate is uncertain, because you know rainfall is spatially variable. At a given time t, rainfall is spatially variable. So if you have only point measurements and you estimate the average rainfall over the catchment as the average, for instance, of this point estimate, there is uncertainty. And this is, as I said, a typical question of hydrology, how to estimate the average rainfall over a catchment. We don't consider this question and the related methods in this course, because this course is a course of advanced hydrology. We already assume, because we want to turn to water resources management, that we have a good estimate of the range of the average rainfall over the catchment. Let me just say that there are methods. The simplest one is you get all the rain gauges over the catchment and you compute the average. This is the simplest method. There are more refined methods based on spatial interpolation techniques. You may have heard in your background of Kriging methods, for instance, to perform spatial interpolation. The concept is essentially the same. You have point measurement and you have to turn them into an average measurement over a given area. This is a classical question also in other disciplines. For instance, in petroleum engineering, sometimes you make some checks of some wells in order to get you know, the consistency of a layer of petrol, and then you get several measurements, several point measurements, and then you have to interpolate them to get an estimate of the average availability of petrol. So it's a classical question in environmental modeling, but of course it's indeed a challenge. Is this clear? Okay, so let me go back now to our model. So it's essential that you notice that this is volume of rainfall over the catchment. This is the first issue that I wanted to point out. And then let me say that we still don't know the value of K. And when we performed our exercise, I mentioned to you that we may try with several values of K. And this is an open issue, and we will consider it as soon as we get to probably within 15 minutes. Now, let me just clarify what happens. I already mentioned very briefly what happens when rainfall is assumed to be constant. I want just to analyze with more details this case. So let's suppose, let me write here the relationship that is written there, which gives to you, according to the linear reservoir model, the river discharge. So it's QT. Let me use the same symbols. It's QT is equal to the integral between 0 and t of 1 over k e to the power of minus t minus tau over k multiplied by p tau in the tau. Let's forget about the depletion term. Okay, let's forget it. Let's assume that Q0 is 0. And this is our relationship. I think the symbols are, everything is okay there. Okay, now let's suppose that rainfall is constant. So this is constant. And then we can bring rainfall outside of the integral sign, and we can write that Qt is equal to, also K can be brought outside the integral sign, so Qt is equal to P over K. P doesn't depend on time anymore because it's constant in time. So it's P over K, which multiplies the integral between 0 and t of e to the power of minus t minus tau over k in the tau. So this is the integral that now we have to compute, and this can be analytically computed. First of all, let me bring, we can write e to the power of minus t minus tau over k as a product of two terms. So let me write it. So this is equal to p over k integral between 0 and t of e to the power of minus t over k times e to the power of tau over k in the tau. So we can split this e to the power of minus t minus tau over k in the product of e to the power of minus t over k times e to the power of tau over k. And now we recognize that this term here, this is constant, and therefore for a given time t, this is constant, and therefore we can bring it outside of the integral sign. And then we can write that Qt is equal to p over k times e to the power of minus t over k integral of between 0 and t of e to the power of tau over k in the tau. And then we recognize that this integral can be easily computed. I propose to go to the upper side of the MacBook. I think it would be better if I turn the light on, at least here. See. And also let me open a window here. I think it's better if we open this one, it's less direct to you. Let's try. So let me delete to the upper part of the blackboard and move forward. So basically Qt is equal to e over k e to the power of minus t over k. The integral here, computed between 0 and t, is, I think it's k e to the power of tau over k. Let me, yes, I think it is fine. And then I can rewrite the first part as it is. So t over k, e to the power of minus t over k. And here, we have k e to the power of t over k minus k. It's clear so far. If I'm going too fast or there is something that you don't understand or you cannot see where, just stop me, okay? These lectures should be like discussions. Don't be afraid to stop me and ask questions. Okay, now you see that we can eliminate k here. And we are almost there. And let me rewrite on the left side of the blackboard. So I delete here. Okay, so basically what we get is P times, now, e to the power of minus t over k times e to the power of t over k is 1. 1 minus, this is 1, so it's just minus e to the power of minus t over k. Which is nice. Let's draw a graph to better understand what is the physical meaning of this relationship. And the graph is basically our hydrograph. What I want to depict is the progress of Qt along time, starting from 0. Now, what happens at time 0? At time 0, basically, between parentheses, I have 1 minus e to the power of 0. So 1 minus 1, which is 0. So at time 0, q is equal to 0. So the graph starts from the origin, which is something that we can guess because we neglected the depletion term. The depletion term is q0, starts from q0. So if you assume that q0 is 0, you expect that at time 0 you don't have any q. So basically, it's fine that we start from the origin of the graph. And now let's understand what's happened for time that tending to infinity. So when time tends to infinity, you see that e to the power of minus infinity is 0. So basically, for time tending to infinity, q tends to p, because inside parentheses we have 1 minus 0. So let me just place p here, and I can put p and q on the same axis because they have the same dimension. One is volume of rainfall and the other one is volume of river flow per unit time. So they have the same dimension. Okay, so I can just indicate here the level of P. And what I see from this relationship, again, is that for increasing time, Q tends to P. So this is something that I expect to be like that. Which is, again, something that we can, you can understand. Because what are you expecting from a catchment if you have a constant rainfall? At the beginning, you have rainfall infiltrating into the soil, and therefore you don't see any river flow. But then the soil gets wet and wet and wet. And at the end of the story, after a long time, the soil gets saturated, which means that it doesn't retain any more water. And therefore you expect, in the long term, that you get a river discharge that is equal to the volume of rainfall over time. This is what our intuition may indeed suggest. And what is the rate, the pace with which we get to this asymptotical value? So it's clear that you may have different graphs here. One is this, but you could have also a graph like this one. Let me make it more clear. So what dictates the speed of convergence? The the speed of convergence can be dictated nothing else than k. So what dictates the speed of convergence cannot be any else than k. Because of course you have here a function which doesn't have a fixed shape. The shape is varying. And what changes the shape of this function? Only k, because any other variable and any other item here is defined. So t is defined basically because you compute the river flow at a given time, rainfall is constant, so just k is varying. So if you have a function which has an overall structure which is unchanged, but the specific shape changes, then it's a clear case in which you have a parameter. You may remember how I define a parameter is an element in a function, is a term in a function which dictates the specific shape, but not the general structure of the function. So this is really one of the cases in which I see that there is a specific shape that changes depending on a parameter value. So it's k that dictates the speed of convergence. And let's try to understand what is the way in which k impacts this speed of convergence. Would you expect a faster convergence with a low value of k or with a high value of k? And when you are asked a similar question, you may reply by following two lines of reasoning, two train of thoughts. One is intuition, and the other one is mathematical analysis. So let's try to start from the mathematical analysis. So basically, you see that if you have a very high value of k, it takes a longer time to get this term close to 0. So e to the power of minus t over k goes to 0 more rapidly if k is small. So I would expect that this is a curve for small k, and this is a curve for bigger k. This is what the mathematical analysis tells us. And now, by intuition, basically by intuition, don't forget that you have a reservoir here, and rainfall is falling into the reservoir, and basically you have a discharge from the reservoir which is equal to W divided by K. So what does it mean, this consideration? It means that if you have a very high value of K, what happens is that in order to generate an outflow, you need much more volume stored into the catchment. So basically, this conceptual scheme with a high value of K ends up with a lot of storage into the catchment. Because in order to get an outflow that is equal to rainfall, you need a larger storage if you have a larger K. So it means that basically if you increase the value of K, you increase your storage in the catchment. But if you increase storage, then you expect more infiltration, which means a slower convergence to a volume of discharge that is equal to the volume of rainfall. So even the physical analysis, the analysis by intuition, confirms to you that if you increase K, you need a longer time to get to convergence, to get the river flow converging to the rainfall volume. It's much important when you have when you deal with a mathematical relationship to emulate a physical process. As I told you, it's extremely important to see the relationship between your mathematical relationship and the physical process. It's extremely important. And in the case of parameters, and in this case you have this parameter k that has the dimension of a time, it's extremely important that you try to understand what the value of the parameter means. Because if you understand the physical meaning, you can guess a value for the parameter. This is extremely important. Because, as I said before, we have the problem of estimating this K value. We don't know it. We have to estimate it. Now or later, we have to estimate it. And therefore, to have a preliminary guess, it's important. Still, you don't have a real guess because, you know, K as a dimension of a time. If I told you what could be a good guess for K for the Po River, you just understood that probably for the Po River you need a large value of K, because I told you that a large value of K means a large storage. So you think to the Po River, and then you realize that a so large basin must have a large storage, and therefore probably you would understand that K is quite a high value, but still you don't know if you had to guess a time. Is a proper value of K for the Po River around 1 minute, 1 hour, 1 day, 1 week? You still don't know. Okay? But what is important is to have an idea of the physical meaning. Perfect. Now, another thing that I wanted to tell you, keep in mind this behavior. Any catchment for long rainfall, long and constant rainfall, tends to deliver a river discharge that is very close to the volume of rainfall per unit time. And the time required to get to this situation is larger if you have a significant storage. So if you have a catchment with a very reduced storage, like an impervious catchment, you get to this equality of rainfall and discharge very quickly. If you have a catchment that is permeable, that gets a lot of infiltration, has a lot of storage, then it's less dangerous, because after a rainfall, it takes a long time before delivering this volume of water that rained over it. You have always to be concerned in terms of flood risk by catchment with a reduced storage. And the reduced storage is given by the catchment being impervious, which means not permeable, or being very steep, because the two things are strictly related. If you have a steep catchment, it means that water runs very quickly over it, doesn't have time to infiltrate, so infiltration is reduced. And also there is to say that if a catchment is steep, probably you will find rocks over the hill slope, not permeable soils, because you can understand that if a soil is permeable, then it's eroded in the long term, and the slope of the hill slopes decreases for the effect of the erosion. So all these physical meanings and physical behaviors of catchment need to be really, you need to really get familiar with them, because they allow you, by looking at a catchment, to gain a preliminary idea of its functioning, which is, as I said, extremely important to gain a preliminary judgment, a preliminary guess of your results, a preliminary intuition of what your results should look like. And also an impervious catchment with the reduced storage is also a concern for the water resources manager, because it means that you don't have water stored in the catchment after a rainfall. It means that it rains over the catchment, rainfall flushes away, and after rainfall you don't have any storage left. And therefore, if you need to find water, if you don't have storage, you are much more concerned. Okay? Also, this consideration allows you to better understand why, when one is concerned about floods, sometimes a solution is building a dam. Why is that? Because people, through the storage of the dam, they can retain some water, and therefore, the flood is mitigated. Because, of course, if you have a heavy rainfall over a catchment, and you are able to retain some water, it means that the river flow is lower, and therefore the flood impact is mitigated. But this is perfectly responding to our reasoning. You increase the storage, because by increasing the storage, you reduce the river flow. At least in the short term. Okay, perfect. Yeah, please.
Like cassa d'espansione?
Yeah, like cassa d'espansione, which means in English is retention ponds. So you build retention ponds because you want to increase the storage of the catchment. And this is for flood retention, but also for water resources management. Sometimes they are used for a double purpose. You create some storage for mitigating the impact of floods, and then you use this storage to collect water to be used during the dry season. Okay, perfect. Now, let me now move to the next slide, where you see a generalization of linear methods. Any linear model, any linear rainfall runoff model, and we considered two linear models so far. The linear reservoir, which we analyzed in detail, and the time area method, which I told you that you are expected to have a look by yourself. These linear models can be written in a general form, and the general form is what you see here. So let me see if I still have, no, I don't have it. So let me write again the formulation of the linear reservoir and show you how we can turn to the formulation that we know of the linear reservoir to the formulation that you see on the slide. So basically our formulation was, let's forget about the depletion term. The depletion term, by the way, is, no, it's not here, so let's forget it. So we have the linear reservoir expressed as the integral between 0 and t of p tau 1 over k e to the power of minus t minus tau over k in the tau. So this is our formulation of the linear reservoir. Now let's call this term here, this term 1 over k e to the power of minus t minus tau over k. What is this? This is what in mathematics is called a transfer function. Transfer function or transfer operator. Basically, this is the term that actually transforms rainfall in river flow. You see, basically, let's forget about d tau. This is just the integration variable. What does this transfer function do? It is multiplied by rainfall to give river flow. So it's, you can understand the meaning of transfer operator. Okay, and this is linear because it's like this term. It's like giving to you the coefficient of a linear combination. So this gives to you the coefficient which, multiplied by rainfall, gives to you the river flow. And this is also called, this can be indicated with a more compact symbol, and here you see H, it's used, H tau. So if I accept this substitution of this transfer operator, if I accept to indicate it with H tau, I can rewrite this integral in this compact form, integral between 0 and t of p tau H, to be more precise, this is H t minus tau. Okay, t minus tau, because the argument here is t minus tau. So h t minus tau in the tau. So this h is called instantaneous unit hydrograph. Instantaneous unit hydrograph. also indicated in the literature with the acronym IWH. Sorry, the IUH, not W, but single U. So basically it can be proved that any linear model can be written in this compact form. So any linear model can be written in the form that you see here and you see there over the slide. What is changing when you turn from one model to another is just the shape of H. That's it. So basically for the linear reservoir you have for H this expression relationship that you see here. For the time area method, it can be proved that there is another relationship for H. For any linear model, you find, for any given linear model, you may find a relationship giving the value of H, depending on time. And then, as I said, it can be proved that this compact form is valid for any linear model. You may say now that there is a difference between these two relationships, because here you see that precipitation, rainfall, is computed, it's taken at time t minus tau, and the instantaneous unit hydrograph at time tau. Here you see that they are inverted. You have precipitation at time tau, and the instantaneous unit hydrograph at times t minus tau. They are the same relationship. You can turn to one to another with a shift of variables. It's very simple. And so don't be concerned by this. And if you try to compute this integral with a summation, if you are not convinced by what I'm saying, that they are the same relationship, I invite you to try to compute this integral with a summation by using like just 5 time steps of rainfall, and you will see that you don't change your result if you use this relationship or if you use the relationship here. They give the same result. Just try and you get convinced. Okay? What I just obtained if I change the variables is an inversion of the terms that are summed.